Hi. Oh, crikey. Sorry about that. Hi, I'm Leif Bergsman, and today I'm here to talk to you about everything. Everything that has happened, everything that will happen, everything that is happening right now, and everywhere it does happen. In other words, I'm talking about space-time. First things first, though, I need to check with the HAL 9000 computer from 2001, A Space-Time Odyssey. You may have heard of him, you may not have heard of him. Anyways, how's it going, Hal?
Everything is going extremely well.
Thanks.
Goodbye.
No problem. When you think of time travel, you usually think of like a science fiction gadget in the very distant future, say like the Doctor Who TARDIS or the DeLorean from Back to the Future. But you don't usually think that it's possible, real people, like real cosmonauts and astronauts, to have a world record for most human time travel. But it's true. People have traveled through time. It's really awesome. It's all thanks to one effect on the big on science theory of relativity called time dilation. Time dilation is, to quote a Wikipedia story, I just need to say this in a authoritative voice. In a theory of relativity, time dilation is the difference of elapsed time between two events as measured by observers either moving relative to each other or differently situated from a gravitational mass or masses. In English, that means that if you take two clocks, keep one on Earth, take the other to space, and take the one in space back to Earth, the time is going to be different. This is not because, say, a mechanical error in the clocks. It's because of the very nature of space-time itself. If you want to feel the space-time continuum, become an astronaut. Because the problem is it's not problem, it's a really cool thing. The thing is with space-time is that time passes slower when you're further from a center of gravity. Like literally, on our Earth, time is passing kind of faster because we are on Earth, because Earth is like a really big center of gravity. But say you're way out of Earth, say on the International Space Station, you're traveling through time when you're actually on there. I kid you not, you can't feel time going slower when you're on the ISS, but when you're actually on there, time is going slower for you. So, let's just say I'm on the International Space Station. I'm going to be there for 80 years. Back on Mission Control, they think I'm going to do it for 80 years. So I'm going to set my clock. In 80 years, it's going to remind me to get the heck off the space station. So with Mission Control is going to set their clock for 80 years. But I, up in the ISS, I'm going to set my clock for 81 years. And my clock and the space station, that Mission Control's clock, they're going to go off on the exact same time. That's only because time changes when you're far away from a big mass of gravity. But thanks to time dilation, the core of our Earth is 2.5 years younger than the crust of our Earth. Which does make sense. It's a bit of a paradox. Because it would be impossible for the core of our Earth to be 2.5 years actually younger than the outside of our Earth. That's true. Because we have calculated this. Say you were going to the ISS for 6 months, you would have aged 0.005 seconds less than everyone on Earth. The person that holds the record for most human time traveled is the cosmonaut Sergei Konstantinovich Krikalev, who beat the previous record of 20 milliseconds of time traveled by another cosmonaut, and his name was Sergei too. This time it's Sergei Avdiev. Yeah? What is it, Hal?
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
This happens all the time. You see, there is this popular movie from 1968. It was called 2001, A Space-Time Odyssey. In the movie, there is a really awesome spaceship. On the spaceship, there is this cool computer. You may have heard of him. His name was HAL 9000. Like, for example, like, I don't play it myself, but if you were to play Lego Dimensions, on one level, like, HAL 9000 actually comes into the game for a few seconds and talks to another robot. But this, like, HAL 9000, he's actually pretty cool. He had, like, in the movie, he had a male voice, and to quote HAL, like, he's a really, really good, like, big supercomputer. But to quote HAL himself, he was foolproof. Although, later in the movie, HAL kind of went rogue and started killing the astronauts and doing really stupid stuff. We have a clip here.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, Hal?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, Hal.
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
Where the hell did you get that idea, Hal?
Dave, although you took very thorough precautions in the pod against my hearing you, I could see your lips move.
All right, Hal. I'll go in through the emergency airlock.
Without your space helmet, Dave, we're going to find that rather difficult.
Hal, I won't argue with you anymore. Open the doors.
Dave, this conversation can serve no purpose anymore. Goodbye.
Hal? 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 Hal?
But the problem is that I have a HAL 9000 over here in the studio, and he still thinks that I'm Dave, and he still thinks that I'm going to disconnect him. And it's really annoying. I actually think I very well might disconnect him. That did it. That'll do it. Anyways, now it's the theory of relativity. Einstein, he started his work on the general theory of relativity in around 1907, which was a time when most scientists thought that the force of gravity had already been elucidated by the works of Isaac Newton. As most high school students everywhere will tell you, in the late 1600s, Newton came up with his alleged universal law of gravity, which had the very first mathematical description of this so well-known force. His law was actually so precise and accurate that NASA engineers still use this information to extrapolate the trajectories of spacecraft and other flying objects. And astronomers, they still use it to predict the motion of stars, comets, and even entire galaxies. For almost a decade, Einstein was completely focused on finding the underlying mechanism, the mechanism that underlies gravity. Because the thing is that nobody really knows, until Einstein's work, of course, nobody knew how gravity worked. In Newton's alleged law of gravity, his alleged, and in that law, it says plain out, he has no idea at all. No idea of how gravity exerts its force. He has no idea, and it says he's going to leave that to the consideration of the reader. And those that are willing will just read on. He doesn't actually know. It's kind of silly. And in 1915, he proposed an answer to the question of how does gravity utilize its force over empty space. The emptiness of empty space seemingly left everyone empty-handed. Pun, yes. But there is something in empty space. The thing in empty space is space. Space is an empty space. Because space is an empty space. Because space is space, so space is an empty space. Einstein then suggested that space itself is what gravity used to pull on things. Here's this idea. Imagine taking a marble and rolling it across a big, flat metal table. Because the table is flat, the marble is going to roll in a straight line. But then, let's just say a fire then burnt up the table. It's a metal table, so it won't burn up fully, but but it is gonna like make it all like warped and rutted and have all these ruts because it's like a half melted metal table. If you roll a marble across that table, the marble will take a different path because of the warps and ruts. The table would like canalize it in a different way. Einstein claimed that the same concept applies to space. A completely empty space, like totally empty, is a lot like the flat table, where objects can go like wherever they please. But the presence of huge bodies, such as stars, affects the table's surface. The sun, for example, creates a bulge in its area. Like, I'm serious. It actually, like, in a space-time continuum, like, parts, like, bodies with a lot of gravity, they create a bulge in the space-time continuum. Anyways, the sun creates a bulge in its area, much like a metal bubble burning on the hot table. And just as the table's curved surface guides the marble along a curved linear path, the curved shape of space, due to the sun, thanks a lot, sun, around the sun, guides the Earth and other planetary bodies into orbit, orbiting around the sun. Now, we're to wormholes. The term wormhole was coined by theoretical physicist John Wheeler in the 50s. A wormhole is technically a link in two different points of space, like say point A and point B. You could use a wormhole for a lot of things. For like, like a wormhole could be a link in 2 points in our space-time, or a wormhole could be a link between this universe and a separate universe. And like, I'm not talking about universe as in like our group of galaxies. Like, I'm talking about like parallel dimension. It like theoretically could. A wormhole's been like, you could use a wormhole for a lot of things. Like, for example, one use you could have it for as a space-time subway. You could like say, oh hey, I need to get to school really fast. Let's have a wormhole in my house and a wormhole at the school. You walk through the wormhole, boom, you're at the school. It's kind of cool. But what's also cool about wormholes is they're like links or like rifts in space-time. And remember, space-time, it goes through time too. So you can have it as a time machine. You say you can have a portal right here, and like you can go wherever you want. Like say, hey, you could go back and like stop the 9/11 attacks if you had the wormhole over there. Although we'd love to show you a picture of a wormhole, but we can't for two reasons. Reason one, it's impossible to have a hole. Like, it's possible to show you a picture of a hole. A hole is the absence of what surrounds it. It's impossible to show you a picture of just a hole, because a hole is the absence of what surrounds it. Contrary to what your local donut shop will tell you, because your local donut shop you will pay $2.99 to buy some donut holes, aka Timbits. So technically, like Timbits are oxymorons. Anyways, reason two is that we haven't found any wormholes in our entire universe. So it would be kind of hard to show you a picture if we don't know that it even exists. So you see your dilemma. Anyways, wait, what? Really? Already? Oh, I'm already supposed to be gone by now. Out. Finito. Done the show. That was short. Well, not really. I've had to take upwards of 20 takes for this video. But anyways, my producers say I still have to conclude this video. So, I guess to conclude this video, does time travel exist? Theoretically, yes. You can use time dilation on the ISS, but physicists are still arguing about if the laws of physics actually allowed on a macroscopic scale. That is, microscopic being really, really small, macroscopic being real, like as big as real life. Like, say, like all humans are macro. Could you survive a wormhole? No. Theoretically, you die if you went in a wormhole. Sorry for that really bad truth. It's theoretically you would die if you went in a wormhole, but nobody really knows. We've never actually seen a wormhole, so we don't know. Now, could you use time dilation to prevent aging? Yes, you could. It wouldn't be that fun. So, putting all this together, with the current understanding, based upon the theory of relativity, we could, I guess, theoretically travel time. But that would be really painful. So I hope you learned something about Einstein's theory of relativity and time travel. Until next time.